reaction.
Hello, this is Masa-aki Haga. Today, I focus on the electrocatalyst for hydrogen evolution catalyst, HER for short. The SDGs, Sustainable Development Goal, call upon us to achieve a wide range of goals as listed in 17 terms until 2030, including transforming lifestyles, reducing social inequalities, ensuring equal educational opportunities, pursuing health and peace, preserving global warming and disasters, and protecting our ocean, forest, and global environment. Each country in the world is expected to work together the SDGs to ensure the health, safety, and peace of its people and to preserve its unique cultures. All stakeholders are expected to do their part to address socio-economic, environmental issues in integrated manners. Scientific research is also no exceptions. The SDGs are not the end of the story until 2030. Rather, they're the first step in a large movement that will last for generations to come. How to reach these goals as electrochemist. Building sustainable clean energy system is one of the most important problems. Traditional fossil sources of energy such as coal and oil are all carbon positive and emit a lot of carbon dioxide, a cause of global warming. Green hydrogen production by electricity-driven water splitting has become a promising strategy. Solar and wind power has become popular in these days, but these renewable energy sources that come from nature are fluctuated with the climate. Recently, they sometimes provide excess power during the day. This figure shows how the energy grid system is coupled with electrolysis with electricity generated from solar and wind when the over generations. Electrolysis stands out as a means of storing electric energies in the form of stable chemical bond as the commodity chemicals. Here again, the similar figures for schematics for energy storage and utilization from simple molecules such as water, carbon dioxide, and nitrogens. Electrocatalysts play a key role in these energy conversion technologies because they increase the rate, efficiency, and selectivity of the chemical transformation involved. The combination of theoretical and experimental study has proven to be successful strategy in this respect, yielding a framework to understand catalytic trend that can ultimately provide rational guidance towards development improved catalyst. For instance, the water splitting reaction, which consists of the hydrogen and oxygen evolution half reaction, has attracted great attention as a sustainable source of hydrogen. So, we focus on the hydrogen evolution reactions called HER as short by using electrocatalyst. Regarding the electrocatalyst for the electric process, there are three factors to control the reactions. That is electron transfer kinetics at the electrified interface, mass transport of reactant and product, and ion transport. Electron transfer process across the electrode interface govern the kinetics of oxidation and reductions, and mass transport for the reactant and the rate at which the product can be removed. Both electron transfer rate and mass transport flux are proportional to the current. Electrolytic water splitting is not only the uphill reactions, as reflected by the positive value of delta G gives the free energies, but also has to overcome a significant kinetics activation barriers. Active catalysts play a crucial role in lowering the activation barriers. This figure shows the transition state energy profile and current potential IE curves for HER and OER reactions. Considering the free energy curve, including the overpotential ether, which free energy delta G becomes lower when inducing the acceleration of reactions. On the other hand, from the current potential curve, Tafel slope and exchange current obtained from zero overpotentials are two important parameters. The Tafel plot has already been mentioned before, as shown in this equation. When the logarithm of current values are plotted over a small range over potentials, the slope of the Tafel plot B is related to the reaction mechanism of the catalytic reactions. With a small slope showing a large increase in the current density as over voltage change, the small slope indicates a very rapid electrocatalytic reaction rate. The intercept A is the current density at zero over voltage, and the larger the intercept A, the faster the charge transfer rate and lower the reaction activation barriers. Two catalysts are shown here in comparison to ideal systems. Tafel plot for the blue and black current potential curves are shown in the inset. Comparing the two blue and black plots indicate that the black one is a better electrocatalyst. HER is a key half reaction to produce dihydrogen at the cathode in water electrolysis, which involves two electron transfer process. The mechanism of this HER is highly dependent on the environmental conditions. As shown in the following equation, on the electrocatalyst surface, the reaction can be divided by the following elemental process. In acidic medias, there are three possible reaction steps. The first step is called Farmer step to produce absorbed hydrogens on the metal electrode. Then the hydrogen absorption reaction can proceed by Arrowski step or Tafel step, or both of them, to produce dihydrogens. For the HER reaction in alkaline media, there are two possible reaction steps, that is, Farmer step and Arrowski step. Electrocatalysts that efficiently react HER in alkaline solution are the current #1 target of water electrolysis method for industrial applications, because alkaline water electrolysis often used more abundant and low-cost materials such as nickel and steel as the catalyst, making it commercially attractive. I have already discussed the under potential deposition of hydrogen on platinum electrode, as shown here, in the case of polycrystalline platinum electrode in 0.5 molar sulfuric acid. When the potential was swept to the cathodic potential directions, two peaks for hydrogen absorption and desorption were observed in Cb. In this case, present surface catalyzed electrochemical reduction of proton to form hydrogen gas. HER has different activation energies and kinetics compared to under potential deposition process. Theoretical calculation revealed that HER activity was related to hydrogen adsorption HAD. The free energy of hydrogen adsorption delta GH is descriptor for the hydrogen evolution materials. The logarithm of exchange current density versus metal hydrogen absorption energies plot show volcano curves. As the adsorption bond energies become larger, stronger absorption of hydrogen on the electrode surface, the reaction rate increased. When the right-hand side, one stronger adsorption of hydrogen on the metal, the loss of absorbed hydrogen needed to larger energy values, resulting in the rate constant slower. In alkaline media, the slower reaction kinetics of hydrogen evolution on platinum hindered the development of alkaline electrolyzers, solar hydrogen cell, and alkaline fuel cell. The HER exchange current density in alkaline solution can be correlated with calculated hydrogen binding energies on the metal surface by a volcano type of relationship. As shown here, HER activity varies by several orders of magnitude from platinum at the peak of the plot to tungsten, wolfram, and gold located on the bottom of each side of the plot, similar to the observed in acidic media. Reducing the use of precious noble metals such as platinum and iridium metals, the non-noble metal-based electrocatalysts pay attention. The exploration of transition metal phosphide TMP is one of the rapid growing areas in developing electrocatalysts with high catalytic activities and stability in both acid and base conditions. It has been proposed that phosphorus atom play a significant role TMP due to the excellent conductivity and unique electronic structures. Here shows nickel 2p nanoparticle structures, which is the two-dimensional seed structures, and current potential curves. Nickel 2p show high HER activities as shown here. The discovery of nickel 2p catalyst as one of the best practical catalysts for HER This study was motivated by the natural enzyme nickel iron hydrogenase, which is higher activity than platinum metals. Further, the metal free energy of atomic hydrogen bonding to the molybdenum disulfide edge is close to that of platinum. This finding identified molybdenum disulfide as a promising electrocatalyst for HER. Also, cobalt sulfide also shows high HER activity as shown here. Among the three different morphology of cobalt disulfide, the nanowires show the highest HER catalyst performance and stability, which attribute to the high effective electrode surface area and high speed. The natural enzyme catalysis inspired chemists to mimic the functions. The proposed catalytic cycle of iron-iron hydrogenase for oxidation of hydrogen and reduction of proton are shown in here. The heterocleaved binding of free ion center and nitrogen site worked on the cooperated manners in the cycle. The proton is picked up by nearby nitrogen base, which is conveniently positioned above iron, so the pathway is mimicked by the recent model artificial catalyst systems. Substrate and product, proton, electron, and hydrogen needed to transport cooperatively through the peptide matrix to form the active site. This transport is highly regulated, and iron-iron hydrogenase have dedicated substrate and product channels, as well as energetically highly tuned electron transport chains. Next, I'd like to move the molecular electrocatalyst and introduce you a system of homogeneous molecular catalyst dissolving solution. The example listed here have been studied as the activation electrocatalyst for small molecules. The catalytic reactions include HER, OER, ORR, and CO2 reductions. Some of the catalysts were designed inspired by enzyme in living systems, and some of the reactions have been tested. First, let us consider what change occurred on the cyclic Boltzmann when a substrate is added to the electrocatalyst dissolving in solution. In the reversible electron transfer reaction between P and Q as P process, observe the reversible wave. When reactant A is added externally, a redox reaction occurred between Q and A is converted reactant the product B. At the same time, Q returned to the original P. Therefore, the reaction cycle takes place catalytically. In other words, in CB, as A is added, the reduction waves of Q disappeared and oxidation current value P increased. When sufficient amount A is added, the limiting values is reached. Since the Cv of the Ec prime reactions in electrocatalytic systems varied greatly depending on the chemical reaction rate, a detailed theoretical study was conducted to plot the ratio of the scattering rate of the reaction rate as lambda and the ratio of the added substrate and catalytic concentration as shown here. A zone classification diagram has been created. Corresponding the various zone Cv shapes are shown in the small box below. I will discuss how to estimate the reaction rate from the analysis of the system that gives the limiting current case when substrate are added in electrocatalytic systems. First, we will summarize the information on overvoltage and kinetic current values. The ratio of the limiting current value without and with catalyst can be expressed by this equation. Then we can calculate K ohms from these equations. As a case study, I pick up the analysis of Cv of nickel complex catalyzed HER in solution, in which 136 triphenyl 1 other 36 diphosphorocycloheptane PNP is coordinated to nickel with a different number of surrounding coordination ring size. A nickel divalent monovalent reduction waves is observed at about -1.1 volt. When trifluoromethylsulfonic acid solution in DMF is added to the solution, the wave becoming irreversible and the catalytic waves appeared. Current values increase with the amount of the acid, as shown in this figure. Based on the ratio of these current values, the reaction rate can be determined and turnover frequency can be calculated. Here is a summary of today's talk. First, I just will introduce the design of electrocatalysts play a major role in HER reaction to minimize the overpotentials and improve the energy efficiencies. Second, I introduce new trend from noble metal-based such as platinum or iridium to non-noble metal-based electrocatalysts such as using nickel or copper or molybdenum has been introduced. And the final part, I just pointed out the molecular electrocatalyst. Mainly, I talked to the analysis of catalytic Cv for molecular electrocatalyst was discussed to determine reaction rate. Also, Cv shape is determined by the reaction rate in the zone classification diagram. So I think this information gives the important step to understand HER reactions. Finally, I listed the reference for today's talk. Please read this reference if you're interested. So this is the end of my talk. Thank you for listening.
Thank you, Professor Haga. If you have any question regarding the lecture, you can contact us. The next webinar, the Professor Haga 13th lecture. For the moment, we are planning to schedule for August. The detail will be updated in the beginning of next month in the ALS website. For today, thank you and have a nice week.